This section is titled Structural Barrier Shielding. This is the last set of notes for you guys. This sort of puts the capstone on everything for personnel protection. So we're going to talk about what are our structural shields, what are the requirements, where are they, that kind of stuff, and we'll get names for all these structural shields. So let's go ahead and jump into this. First off, the typical X-ray suite, called a fixed X-ray suite, a room that the X-ray machine is kept in one place, doesn't leave the room. All the X-rays are done inside that facility. You're going to have shielding built into the building, built into the structure of the room. There's two types of shields that you'll find built into structures: primary shields and secondary shields, or we call them barriers. So primary barrier and secondary barrier. The difference is, a primary barrier is any wall, floor, ceiling, anything in the room that the X-ray tube can be pointed directly at, okay? Primary barriers are barriers that the X-ray beam strikes during normal use. The primary X-ray beam hits primary barriers. So you guys know, like the wall bucky, right? That we have to turn the X-ray tube and point it at the wall bucky. Well, that wall behind the wall bucky is a primary barrier. Okay. If your X-ray tube is pointed down towards the floor and you're on the second floor of a building, then your floor of that building, of that room, which is the ceiling of the room below, that floor is a primary barrier. Okay. Secondary barriers, radiation only strikes them after it has scattered. So the primary X-ray beam cannot be pointed at a secondary barrier. Remember, X-rays travel in straight lines, right? So if the X-ray beam cannot be pointed at a barrier, then it's going to be a secondary barrier only absorbing and only blocking scattered radiation. Your control booth is a secondary barrier. So here's the rule. The rules, two of them. Primary barriers must be 1/16 of an inch of lead, or it's 1.5 millimeters. 1/16 of an inch. Secondary barriers are half that. 1/32 of an inch, which is half of 1/16, or 0.8 millimeters, which is roughly speaking half of that 1.5 millimeter. So that's our requirement for thicknesses for our primary and secondary barriers. Secondary barriers are half as thick as primary barriers because they're not designed to be hit by the primary X-ray beam. So here's an example, two examples of control booths. And you'll notice for this control booth here, so we're standing inside the X-ray room right now. Basically the X-ray table would be like right behind us for the person taking this picture. We're facing towards the control booth, and on the other side of that wall, that partial wall, the X-ray tech would stand to make their exposures. They have a window to look through. That window is made of leaded glass, and you'll see a little rack on the wall to hold those blue shields, okay, those blue radiation shields. But anyways, notice that barrier doesn't go, I can scroll down just a little bit, doesn't go all the way to the ceiling, right? It's only required to extend to 7 feet high, as I said earlier. Hard to tell in this one. This one, roughly, yeah, it's hard to tell because of the picture, but kind of looks like it doesn't extend above where the windows are, maybe. The pictures might be a little optical illusion, but the point is, regardless of how high the wall actually goes, the shielding in the wall only needs to extend up to 7 feet. So the wall may very well go all the way to the ceiling, but the lead will not continue past 7 feet.
Why would, like, if one of the doctors decided to have the whole...
Sure.
Why would he want the whole thing?
Be extra safe, so it's just going above and beyond. If they did more than what was required, they'd be going above and beyond. Now you'll probably see a lot of rooms where the wall actually goes to the ceiling, right? But if you were to check behind the drywall and look for the lead would probably stop at 7 feet. There'd be no good reason to continue the lead beyond 7 feet because lead's expensive to work with, and it's sort of a difficult material to fix in place, so you don't need to put it up higher than 7 feet. You could, though, if you wanted to spend the extra money, have your facility be a little extra protected. But yeah, only 7 feet high, okay? And as you probably have noticed, most radiographers are not 7 feet tall, right? So if we were taller than 7 feet, our head would be above that 7 foot height, right? But you're just not finding any radiographers that tall, so it's sort of by convention that we set that height. a normal sheet of plywood or drywall is an 8 foot by 4 foot sheet, so 8 feet tall. Okay, they could have made it 8 feet. They made it 7 feet for whatever reason. It doesn't really matter the reason necessarily, but 7 feet high means the beam would have to have scattered twice before hitting you. Okay, and that's the important part. All right, these lead sheets, these leaded sheets come in big rolls of lead that they use, that they unroll it and they put it up on the wall, fix it to the wall. But anyways, these lead sheets have to butt together, right? They put them on the wall, they butt together. If they just butted together like that, there would be a small space between them where X-rays could pass through. So the leaded sheets have to overlap. Okay, they have to overlap by 1 centimeter. So just 1 centimeter is roughly the width of your pinky nail. So those leaded sheets can't just touch each other. They have to touch each other and overlap each other by a little bit. Okay, that prevents the joints between sheets from being a place where X-rays can pass right through. Okay, lead is ideal. Lead is the ideal thing because a small amount of lead can absorb a large amount of the X-rays. You can use any material to absorb the X-ray beam. Enough air between you and a source of radiation would absorb the X-ray beam, right? That's basically just distance, right? So distance could be, you could have enough distance in between you and the X-ray beam to absorb it. The point is that any material potentially can act as a barrier. Okay, as long as you have enough of it, right? You can take a foam, right? Big blocks of foam, and as long as you have enough of these big blocks of foam between you and the source of radiation, you're going to block enough of it. Okay. So you can use any material as long as you use enough of that material to be equivalent to lead. Okay, so alternative shielding materials include the specialty leaded glass we use. Usually a 1/4 inch thick of leaded glass is equivalent to about a 2 millimeter thick sheet of lead. And if you remember our requirement for lead primary barriers, the thickest possible barriers, was 1.5 millimeters. So these leaded glass windows are more than the required thickness. Regular glass. Regular glass absorbs like concrete does. Okay, concrete does a pretty good job, but you would need 4 inches of concrete to work the same as a 1/16 inch thick sheet of lead. Okay. Cinder block. Where do we have cinder block? Like these walls here, these cinder block walls. Those cinder blocks are about 4 inches thick. Okay. You have to take into account also that there's air pockets in them, things like that. But roughly speaking, a cinder block wall is about the same amount of thickness about the same amount of absorbing ability as a 1/16 inch thick sheet of lead is. Okay. So if instead of a 1/16 inch thick sheet of lead, you had a cinder block wall as your primary barrier, that would be fine. Okay. The NCRP says, though, try not to use concrete for barriers. Try to use them as little as possible because concrete's sort of hard to predict. It gets air pockets. One concrete wall will not be exactly the same X-ray stopping ability as another concrete wall. Concrete's different types of concrete. So, but roughly speaking, a 4 inch thick piece of concrete is about the same as a 1/16 inch thick sheet of lead. The air pockets make big problems. So that's one thing though. Masonry. What they mean by masonry is bricks. Okay, so like red brick. Okay. A 4 inch thick brick, which is roughly how thick bricks are, right? So a brick wall will be about 4 inches thick. Brick's a lot denser than concrete is. It's heavier. And so a 10 centimeter or 4 inch thick brick wall is about 1.5 centimeters of lead, or 15 millimeters, which is a lot more. That's 10 times more than the thickness requirement. So masonry is fantastic. Brick walls are fantastic shields. Why don't we build things with brick that much anymore? Earthquakes are probably the primary example, right? They're great. Brick is very strong. It's fantastic for absorbing X-rays. It's also really pretty easy to build with, okay? You make bricks out of lots of different things, so material's easy to get. But it's structurally very strong until you start to shake the structure. Okay, so we don't build things out of brick really because of earthquakes, as well as other places, hurricanes and things like that, twisters. But anyways, we try to avoid brick. masonry, but it's a fantastic barrier, 10 times the absorbing ability of concrete. Gypsum board. Gypsum board is a drywall. Okay, so that's brick wall, but like not this wood, but above the wood, that's drywall, right? So the stuff that your homes have for their walls, that kind of thing, right? Drywall. Drywall has enough absorbing ability to work as a secondary barrier, but it's not dense or thick enough to work as a primary barrier. Okay, so it would be okay as a secondary barrier. Okay, so we have alternative materials, right? One of the most important alternative materials is the leaded glass, by the way, okay? The leaded glass allows us to have something that we can see through. Think about it like this, right? All the other materials that you know of that stop X-rays also stop light, right? Like lead and brick and concrete, right? They all stop light. Light doesn't go through them. You can't see the light from outside inside this room, right? But with a leaded glass window, it stops X-rays, but allows visible light to travel through it. So it's special in that way, right? It stops the high energy stuff, but lets the low energy light, visible light travel right through. Okay. That's some very important stuff about structural shielding, the requirements for primary and secondary barriers. So remind me again, what's a primary barrier? So a primary barrier is any wall or floor or ceiling that the X-ray beam can be pointed at, right? What's a secondary barrier?
Scatter radiation.
Yeah, so a secondary barrier, the X-ray beam cannot be pointed at it, right? It's only hit by scattered radiation. What's our thickness requirement for primary barriers? 1.5 millimeters or 1/16 of an inch of lead. What's our requirement for secondary barriers? 0.8 millimeters or 1/32 of an inch of lead. For whatever reason, and don't ask me why, we use the metric system for almost everything now, but for whatever reason, we still talk about the structural shielding in inches. It's given to you in millimeters, but then in parentheses they have it the inch measurement because we still use that one primarily.
Will this be on the board?
Very much so, yeah. That's why I spend a lot of time on these numbers because, yeah, they'll definitely be on there. Yeah, the 7-foot high thing, that's going to be on your state board exam. The primary, secondary barrier, the definition and the thickness requirement will be on there, I promise you, in one form or another. And all of these other things, like you'll probably want to remember how much concrete is equal to 1.5 millimeters of lead. It's a 4 centimeters of concrete, or 4 inches or 10 centimeters of concrete. So you want to remember these things. It's a lot. I'm giving you guys a lot, but remember that there's a lot more that I could give you, right? So anything that I am putting out there is important stuff to hang on to. Yeah. Still a lot though, right? It gets easier as the more you do this and the more you practice, and a lot of it's repetition. A lot of it's just like remind yourself, because there's no good way to remember these thicknesses aside from just memorizing them, right? Other things, they're a little easier, a little more intuitive, but yeah. Okay, let's move on. Let's talk about radiation areas in facilities that use or will be exposed to radiation within them. There's 2 types of radiation areas. We're going to call them controlled and uncontrolled. A controlled area is occupied primarily by radiation workers. The occupancy must be known, so we know who's going to be in there. We don't let just anybody into our X-ray room. The working conditions must be supervised, and the radiation equipment must be inspected regularly. That probably sounds a lot like your X-ray rooms, right? We're supervised. Who does the supervising? Do you guys know? Huh? Any doctor? It's the S/O thing, right? Supervisor operator, okay? So in the state of California, if you're a physician, you can be an X-ray supervisor, okay? We call you a supervisor operator, okay? You are a physician who went and took a test with the state of California and now you have a permit with the state of California that says, I'm a supervisor operator. What that allows you to do is, it allows you to supervise the use of radiation, so you have supervisory oversight over all of the x-ray tech. You're responsible for their safety. And you are also an operator too, so you can walk in and use the x-ray machine all you want. You're a supervisor and operator, right? So your doc that you work with, right, he's a supervisor operator, so he can operate the x-ray equipment and supervise anybody else who operates it. The supervisor operators are almost always a physician that works for the clinic, and they are almost always, if it's a smaller facility, they are also the radiation safety officer too, the RSO for the facility. If it's a larger facility, you might have a separate person considered the radiation safety officer, and then there's the doctor who's a supervisor operator. Supervisor operators do not have to be in the building to supervise. They just have to be accessible by phone within 24 hours to provide counsel on problems that come up. But yeah, so you guys all of your internship sites, even if you don't work directly with that person, you have a supervisor operator. It's the person who signs your x-ray logs upon finishing them. Barriers in controlled areas must be sufficient to keep exposure rates below 100 microgray per week, 5 milligray per year. That 5 milligray per year is an important number. Where is it coming from? Do you guys remember where 5 milligray comes from? Think back a long time ago to natural background radiation. Okay, but the first radiation safety module. Okay, radiation safety 1. Remember that we're exposed to natural background radiation. How much are you exposed to per year?
2.
It's about 5 milligray. It's 3.5 to 5.5 milligray, but about 5 milligray. That's where this number comes from. Your radiation areas have to be set up so that the amount of radiation that leaks out of those areas is less than the amount of natural background an average person would receive. Okay, we can't be giving people more than the natural background that they're receiving. That's the idea. The opposite is, or the other version is, uncontrolled areas, which are not our X-ray rooms. Uncontrolled areas, barriers must be sufficient to keep exposure rate below 20 microgray per week or 1 milligray per year. So a lot lower. Uncontrolled areas have a lot less radiation use. This would be like if you're a mobile radiographer, right? You go to somebody's like inpatient room or something like that, right? That's an uncontrolled area. Okay, warning signs. There's 2 types of warning signs you should get familiar with. You should know which one's the right one to go outside of your x-ray room. So these 2 types, we'll call one of them caution radiation area signs. This is required if you are in a controlled area. Both of these are required if you're in controlled areas, controlled radiation zones, like our x-ray rooms, nuclear medicine suites, things like that. The caution radiation area is required if exposures can go above 100 millirad for 5 days or 5 millirad per hour. Somebody has to come and measure this, by the way, to decide which you fit under. Our x-ray rooms are just radiation areas, so caution radiation area for our x-ray rooms. In a fluoroscopy or CT facility or cardiac catheterization laboratory, these places that use large amounts of radiation, they'll have a caution high radiation area sign. This is required if the exposure can go above 100 millirad per hour. So more, 100 millirad per 5 days for caution radiation area, 100 millirad per hour is the requirement to have the high radiation sign. This is the sign you should be familiar with, just the radiation area. You'll want to make sure that it doesn't say something like radioactive or anything like that, because our machines are not radioactive. They emit radiation when they're turned on, energized. These are the signs we should be familiar with. The caution radiation area sign, they have the radiation symbol on them in the middle. They say in English, caution radiation area. And these are outside of our x-ray rooms. These are required to be posted outside of any entrance to the x-ray suite. They need to be either red, maroon color, or black symbols with a yellow background, high contrast, so anyone can see it. Must be posted near all entryways to radiation facilities. Alternate options for other like nuclear medicine rooms will have these radioactive signs on them, which is a different thing, a different type of radiation. Okay, so everyone's okay with the idea that there are two types of radiation areas. One's a high radiation zone, the other's a lower radiation zone. Both of them are considered controlled areas. We know who's in them. The use of the area is supervised by a supervisor operator. And outside of these areas, you're going to have either a caution radiation sign or a caution high radiation sign.
It scares people away.
Yeah. Yeah, so you'll want this. You may also have lights that turn on anytime the beam is on, right? X-ray in use kind of sign outside of the room. Those are fine, but the state of California wants this sign posted on all entryways to your room. So if you don't have this sign, you can quickly and easily download these off the internet for free and post them outside of your entryways to your rooms. Okay, advisory groups, radiation safety advisory groups. These are people who make policy, basically. They make recommendations so that the federal, state, and local governments can then make policy. But anyways, you should be familiar with some of these names. One is, one we've talked about already, the NCRP, the National Council on Radiation Protection and Measurements. This is the one who made the statement that I started with this morning. They also make their reports that they produce roughly every decade. The ICRP is the International Commission on Radiation Protection, which is, they're basically the same as the NCRP, but they set recommendations for radiation use internationally between different countries. The NAS and NRC, National Academy of Sciences and National Research Council, they publish a report called the BEAR Report. So these are publications on radiation safety. United Nations Scientific Committee on the Effects of Atomic Radiation. We don't deal much with what they say because most of what they are talking about is natural radioactivity, not the man-made kind that we produce in the X-ray room, but what they're mostly setting regulations for are the effects of natural radioactivity, so radioactive particles, things like that. There are a number of other organizations such as the Food and Drug Administration, Environmental Protection Agency, I'm skipping a few, American Medical Association, as well as the American Society of Radiologic Technologists. These guys are important, the ASRT. You may want to consider subscribing to them. It's a fee, but you may want to consider subscribing to them as an X-ray tech because you can do your continuing education through them, okay? And if you don't know, once you're professionally credentialed, you have your permits with the state, you'll have to regularly, every 2 years, update your pay a new fee, submit continuing education evidence, and you can do continuing education through lots of different companies, but the ASRT is fantastic, and their continuing ed is specific to radiation use. American Society of Radiologic Technologists. Plus, once you subscribe, you'll get their little magazine monthly. It's nice. It's a good read.
Do you have to subscribe?
I believe you have to subscribe to get their CE stuff, as well as the magazine, but you should double check me on that. In case you want to know what the reports look like from the NCRP, here they are. This is what they look like. They're little books, okay? The books will have at the top, up at the top, it'll say NCRP report, and it'll put a number on there. Today we talked about report number 102, and I believe number 116. We gave a note from each of those different reports. But yeah, they're little books, okay? Again, I have 102, and I believe I have 116 here. The others are not as important for us. But like if you look at report 102, medical X-ray, electron beam, gamma ray protection for energies up to, it's like 5 MeV, 5 mega electron volts. But anyways, in this, like 116 says, we're going to talk about in this book the limitation of exposure to ionizing radiation. How do we limit exposure to that, right? So these reports are great. They make recommendations so that the local, federal, and state governments can set policy. Someone's got to do the research, right? These guys are doing the research. Statements come out roughly every decade. Sorry, reports come out roughly every decade. Statements, as we talked about this morning, come out when they need to. Okay. Regulatory agencies, people who make the rules that you have to follow. There are others, but let's look at a few. The Nuclear Regulatory Commission. And so they define states who agree to follow their guidelines versus states who do not agree to follow their guidelines. They call these states that follow their guidelines agreement states, and states that don't follow the guidelines non-agreement states. What do you guess California is?
Non-agreement.
No, they're an agreement state.
Oh.
Yeah, I'm curious. Got to know one way or the other, but yeah. So we are an agreement state. We follow guidelines set by lots of different people. One of them is the NRC, the Nuclear Regulatory Commission. So we follow all the rules that they put out. You can go look up their regulations and see that they fit with state guidelines. Basically, the state of California wanted to make it, and they don't usually like to make things easy, but they wanted to make things easy. And basically, the state of California just says, we're going to do whatever the NRC tells us to do. So the state of California's policy is mostly set by the NRC, okay, the Nuclear Regulatory Commission. Agreement states have more stringent guidelines. The use of radiation is stricter in states that agree to follow NRC guidelines. The BRH, the United States Bureau of Radiologic Health, they publish things like the Nationwide Evaluation of X-ray Trends Study. Good study on the use of radiation. They're a regulatory agency. EPA and FDA are the Environmental Protection Agency and Food and Drug Administration. I know X-rays are not a food or a drug, but the FDA gets to say something about the use of radiation in the United States, so we follow any FDA guidelines. State health departments. Our state health department is the California Department of Public Health Radiologic Health Branch. Okay, so if you want to go look up what the state of California follows for their guidelines, which almost always follows the NRC's recommendations, you can go to California Department of Public Health, Radiologic Health Branch, just Google that. It'll take you to a .gov page for them, and you can look up any guidelines you want to. You can also do things like search who in California has valid and active permits for the use of X-rays. You can search my name, any of the instructors' names, anyone you work with who's an X-ray tech, you can search them, see that they're permitted within California. In California, all X-ray technicians or technologists, even if they're nationally registered, such as myself, have to have a separate California permit to take X-rays. So you guys have to have a California permit to take X-rays, right? It's your state permit that you take a test for. I do as well. Okay, even though I'm nationally registered, we in California always have to have California permitting. It's just the way that California likes to do things. This is not the case for all states. All states do things a little bit differently. Lastly, on this page, OSHA. What or who in the world is OSHA? There you go. Yeah, not something. You got it right. The Occupational Safety and Health Administration. What level of government are they? State, federal, local? Federal, right? Which means they're the United States government, right? OSHA, Occupational Safety and Health Administration. What do they control?
Make sure you have a water fountain.
Make sure you have a water fountain. More broadly, like as a general idea, what do they have control over?
Safety and
Working conditions, right? So they don't just say like, things about the use of radiation. They say very little about that, right? They're the Occupational Safety and Health Administration. They say how to keep workplaces safe for people who work in them, right? Occupational safety and health. They're the ones that require you to wear like hard hats on construction sites, right? And to have your cords covered if they're running across the floor and things like that, right? Exposed wires can't be on the wall. You can't use a rolly chair as a stool, right? That's all OSHA, okay? They're also the ones that set your bloodborne pathogen standard, right? The stuff that tells you to wear gloves if you're going to work around blood and all that stuff, that's OSHA, okay? They try to keep employees safe in all lines of work, not just medicine, okay? But OSHA, they might set like equipment specifications, things like that, make sure the equipment's safe for the workers. Okay. So, standard of practice for radiographers. The standard of practice for all personnel working around radiation is ALARA. ALARA is a philosophy, right? It's an idea that says whatever you're going to do with radiation, make sure you're doing it as low as reasonably achievable, right? Use the least amount of radiation to achieve the goal that you want. The goal is to create X-ray images, radiographs, right? Radiographic images. And your job is to do that with the least amount of radiation possible, right? As low as reasonably achievable. Notice it doesn't say use the least amount of radiation. It doesn't say that. It doesn't say use the least amount of radiation. That would be nothing, right? Use the least amount achievable under reasonable circumstances. Good. Legally, it is not sufficient to show that exposure levels are within the maximum permissible. Rather, it must be shown that all reasonable precautions have been taken to keep exposures to the patient and personnel as low as possible. So it's not okay for an X-ray tech. X-ray techs have a yearly, well, maybe you guys can tell me before I just blurt it out. What's the yearly dose limit for an X-ray tech? A little higher. It's in millisieverts, if that helps. 50 millisieverts, okay? That's the yearly maximum allowable, 50 thousandths of 1 sievert for a year. It's your yearly maximum. It's not okay for X-ray techs to get anywhere near that. Okay, it's not okay for us to approach that and just skate below it, right? We have to show that we're doing everything we can to keep exposures to our patient. By we having to show, I mean within the policy and procedures set up for your facility. It has to be shown that we're doing everything we can to keep the exposure levels to staff as well as our patients as low as possible, not just below the limit, right? By the way, there is no patient limit. There's no one setting dose equivalent limits for your patients. We're setting dose equivalent limits for the workers, but everything we do, we're trying to keep exposure to patients and personnel as low as possible. With the reminder that, why do we bother doing any of this? Because the effects of radiation are cumulative over long periods of time. What does that mean? It adds up, right? It adds up and adds up and adds up. It all counts towards your future, right? Any exposure that we can make to radiation in a diagnostic room cannot cause early effects of radiation. It cannot cause things that happen within minutes, days, weeks, or months after exposure. The things that we can make happen in the X-ray room manifest years, decades after exposure. They manifest at the end of life as lifespan shortening, right? Those types of things can happen, and it's impossible to say if one exposure does it, if many exposures do it, if it's going to happen at all. All we can say is that with an increasing exposure to radiation, either occupationally or as a patient, with increasing exposure to radiation, you increase the likelihood of something happening. We can't ever predict exactly what, but something can happen. More exposure means a greater likelihood. We're getting done a little earlier than I planned, but that's okay. Final word. Every radiographer should have an active role in continuously educating not only him or herself in radiation safety, but also other healthcare workers. You should be the expert in the safe use of radiation in your workplace, right? NCRP guidelines state that the technologists shall be aware of the approximate amount of radiation received by their patients and understand the typical occupational doses for their assignments. I gave you guys, when I gave you your radiation safety binders, if you looked inside those, I forget if I put it in the front of the binder or in a sleeve, but I gave you a page that has doses per exam. Like it'll list an exam and it gives the dose for that exam, and it should have been in that binder. I'll bring it up in a little bit here so you can see the page that I'm talking about and look for it. But that page is important because it tells you what the dose is per exam, and as a radiographer, you you shall be aware of the approximate amount of radiation received by your patients. You should know what your patients are getting on average and understand that the typical occupational doses for your assignment, what they are, our skills and knowledge must be continually updated in medical imaging. So yeah, that's the deal, right? You are the professional in the safe use of radiation, so you should be the one to rely on, right? Okay, let me